All right, 8 a.m. Got lab this week. You should have already made your vegetation tea, leachates. Make sure you bring that to lab. I haven't checked the lab board today, but as I go by it this morning, I'll make sure the door's unlocked. So if you make it and you want to just drop it off in the back, you can, as long as the door's open. We'll get that set up. We're also doing community similarity. So we learned some of our biodiversity measures. The descriptors of a habitat, which included our species richness, our evenness, Shannon's index, Simpson's index, and so forth. That's really good at just describing a single community, a single habitat. But a lot of times we want to compare it, and it's not even comparing two habitats. Sometimes we want to compare it through time. So while those habitats are good for describing at a specific time point, they don't really tell us how it changes, how our communities change. So for that, we're going to look at two different measures, learn how to calculate it. It is what we're going to do the calculations in class. You can do it by hand, not terribly difficult. I know I'll show you how to get it set up in Excel so that it can calculate it for you. One faster than the other? Probably not. I think the speed is in calculating proportions. That's what we'll do this week in lab. Next week, we collect the data on the allelopathy. And then we have Thanksgiving. So. No, we come back. We do have lab. During dinner. Yeah. That last one, yeah. So that one's actually a diaspora lab. That has extra credit implications for the final exam. And that is not just individual labs, it's across the entire class. I believe that's posted. The handout's posted. It's not accessible yet. I haven't made it to that one, but basically the same thing. You can kind of read the pre-lab part for it. We'll talk about that next week, and then you have basically up until you do the lab to design your diaspores, and then we'll go out and test them. All right. We do have an exam next week. Start prepping for it. This is where we left off. So metapopulation. So we were talking about just individual populations, their dynamics. And then we introduced this idea that in reality, we have populations existing as like a spatial mosaic. And they do that because environment's heterogeneous. You've got good habitat and you have bad habitat out there. And our species prefer to live in these good habitats. They also exist this way because of disturbances. Disturbances can take what used to be good habitat and transform it into bad habitat. And then over time, as succession takes place, as regrowth takes place, those habitats can become better for our species. And then lastly, human intervention, human causes can take a big, massive patch of good habitat and basically fragment it into good habitat surrounded by inhospitable habitat. And what we've seen is that we have populations that exist in those good habitats. The conventional wisdom has always been, and this is the wisdom that I learned growing up, was that this fragmentation was bad. And that once we fragment these populations, you're going to make a bunch of species go extinct. But through time, researchers started saying, no, our overall populations actually look pretty stable. When we predict songbirds to go extinct, they didn't. They stayed healthy. When we predict some of these leaf beetles, these emerald borers to go extinct, they didn't. They survived. So then they started looking at these patches and realized, well, our populations actually exist as a metapopulation, which is a population of populations. So we have these individual populations exhibiting in are living and surviving in patches. Some of those patches are good, supports high population sizes, high carrying capacities. Some of them are bad. So they support basically low populations, and these populations regularly go extinct. But due to the fragmented nature of our habitat, each of these patches has the possibility of going extinct. And it has to have that possibility, because if it didn't, then we're not dealing with the metapopulation. So when these things go extinct, then we have to rely on populations from other patches to disperse and rescue our patch. Basically recolonize it, establish a new population. How frequently the extinction occurs depends on your patch quality. So good habitats are less likely to go extinct than bad habitats. They depend on size. So larger sizes are less likely to go extinct than smaller sizes. Those are two main ones. So size and quality, and then the rescuing, how often they get colonized will depend on the fragility of our organisms. So how well do they move? Your distances between the patches, so closer patches will get more dispersers than those distant patches. And we will also have the quality of the corridor. So how good is this area where our organisms move? You know, if it's a good quality corridor, you're going to see more likely to see movement compared to a bad quality corridor. The net effect of all of this metapopulation is that each patch has its own dynamics. Each patch has its own carrying capacity, its own population growth rate, its own life history characteristics, which we'll start introducing today. And each patch has a very real possibility of going extinct. We will see population crashes, but then those patches will get recovered. So while you see a lot of variation, a lot of fluctuation in the individual patches, when we look at all of the patches together and look at the population across all patches, that actually exists as a relatively stable population size. And this is why all of this fragmentation that has happened has allowed populations to persist. They've existed as a metapopulation. So yeah, those individual patches, they showed local extinctions, and people started sounding the warning bell and saying, hey, we have to be concerned. This songbird species is going to go extinct if we don't do anything. And then a couple of years later, hey, that songbird is back in the patch and it's starting to recover. Well, that's metapopulation dynamics in a nutshell. How many of our populations actually exist as a metapopulation, or how many species exist as a metapopulation? It's tough to say. Tough to say. But we know that metapopulations are one way in which our populations can survive this fragmentation and deal with the fragmentation of our habitats. I'm not saying that fragmentation isn't a bad thing, just saying that we've realized that, yeah, that metapopulation is a real thing. Our populations can survive in these. All right, summary for our populations. So all populations fluctuate. They're going to fluctuate varying degrees. Some populations fluctuate much more than others, and that includes the magnitude. You have very large changes in our population sizes, and some can have very small changes in our population size. Our density-dependent factors tend to limit how much we fluctuate, because our density-dependent factors are trying to push us to the carrying capacity. But this doesn't necessarily lead to stability. Right? It can get us there, or it can try to get us there, and then we have all of those density-independent factors at work that's going to start adding the noise. They're going to start adding a lot of these fluctuations. Just remember, though, that these density-dependent factors, they're susceptible to this contingency in ecology. Right? It's hard to predict when all of our interactions are going to change, when the magnitude and the directions are going to change. And so every year, these density-dependent factors, which one's going to be the major one, changes. That adds some of our variation to our populations. And then our density independent adds the noise. We also talked about this density-dependent factors could include factors that are internal to the population. So classic ones that we talked about, classic density-dependent factors, were always like competition or predation, where the number of individuals in our population impacts the degree of competition that we have. Well, we also have things that are internal to the population. So we talked about territoriality as a mechanism. We talked about social stress hypothesis. These are both regulatory mechanisms that can limit population size. Then we talked about we don't have a single factor that regulates our population through all time. You may have a single factor that works at a specific time point while we're looking at it, but they're going to change. That dominant factor is going to change, and we need the long-term studies to really reveal which factors are acting on our population. And then we finished up with this metapopulation and recognized that, yeah, some species do exist as a metapopulation. They get there due to our habitat heterogeneity. Sometimes we get there through human intervention. Intervention is probably not the best word. Human development would be a better term. Key to those populations, asynchronous extinction. So if we have a large-scale weather event that affects all patches all at once, if all patches go extinct, we just make our species go extinct. We need it so that there are some patches that survive, that those patches can then rescue the other patches. They can send dispersers, colonizers to those other patches, and then get them established. So when those new patches build up, that original patch, if it goes extinct, can be rescued. All right? Next one, loaded. We're also going to take that attendance quiz now. We have 2 answers for the attendance quiz. Zero and 1. Numbers 0 and 1. Attendance quiz 0 and 1. I hope everyone has this up here. Attendance quiz 0, 1. We just finished that presentation, populations, population descriptors. That quiz goes live. It was set to go live at, I think, 8:15. I think it might be live. Maybe it was 8:10 instead. You got until Wednesday night, so review the interaction. Take the quiz. See what we get through here. All right, life history strategies. We talked about it. So we're still on populations. Still dealing with populations because the dynamics of the populations, the interactions that the populations experience, are a big factor in our population descriptors. The main descriptors that we're talking about are population growth rates and carrying capacities, because our populations always want to survive, right? The desire to maintain suitable population sizes has led to the evolution of various life history strategies. And what strategies we see depends on our carrying capacity and population growth rates. So our equations are you're going to see a lot of overlap, or at least we can start making predictions about what type of strategies we would expect given our population dynamic curves. So we're going to start with life history strategies and talk about how they are optimized. So what is a life history strategy? This life history strategy is a suite of life history traits adapted in a particular ecological context. Suite of life history traits adapted in a particular ecological context. So the life history traits are characteristic growth of our population, or of our species. How fast do we grow? When do we reproduce? How many offspring do we have? How often do we reproduce? Those are all life history traits. They're things that shape or that determine how our organism's going to live. Right? So the life history strategy is a collection of all of those traits. So all of them together, we refer to life history traits. And then note that it's adapted in a particular ecological context. Because these traits are shaped by selection, if we change our environments, our selective forces are going to change, which means that we can have two populations of the same species exhibit different types of life history strategies. All right, so we can't think of it as one species always exhibits these strategies. No, that's not the case. Our strategies are shaped by natural selection, and the forces of selection are determined by the habitats that we live in, our environment. All right, so life history strategy shaped by natural selection, and they can differ across a species because our species lives in different environments. We're going to talk about three components of the life history strategy. We're going to talk about life cycle, which is a pattern of growth and development of our species. We're going to talk about lifespan, which is how long our species should live. And then we'll talk about reproductive patterns. And the reproductive patterns is a big one because we can talk about the distinction or the strategy between producing quality offspring at the cost of producing quantity, or producing a large quantity offspring at the cost of making them much lower quality. We have the number of reproductive events. We have the number of offspring, number of reproductive events. Parental care goes into the reproductive patterns. When do we mature and start reproducing? All of that is reproductive patterns. Now, moving forward, what I want you to understand is that these are not separate items. All right? They're all linked. They all go together. So we kind of have to take into account all three of these big aspects to better understand how our species is surviving and interacting. So our life history strategy that we see might represent an optimized strategy. Doesn't have to. Go back to our early evolution where we talked about trying to produce the best adaptation. This is the same concept. We have a best strategy that's out there, but we might not be there. So our optimum strategy, or where we're going to try to get to that optimum strategy, represents an evolutionary decision made by the organism based on the allocation of energy. All right? It's not a conscious decision. All right? It's not like us, where we go to the Golden Corral and say, oh man, should I have more of these tacos or should I go for that better liver that's out there? All right? It's not, they don't make that conscious decision. Instead, you've got the phenotypes, you've got the genetic code that's starting to dictate how you allocate energy. And then if you do it better than another organism, then you reproduce, you leave offspring with that same trait. So where is this allocation of energy coming into play? Well, each of our organisms has a finite amount of energy. Right? They consume energy, and then they have a finite amount of energy that they then allocate to one of three processes. So they have to allocate this limited amount of energy to growth, to maintenance, or to reproduction. Right? They're going to allocate this energy to this three processes. How they allocate it, or the quantities allocated to each one, is that evolutionary decision. So those that make better decisions towards their allocation will do better. So the energy that we have, if we allocate it to growth, it's going to affect things like our growth rates. It's going to affect things like our overall size. Maybe it's going to affect some of our, you could say plumage, if we're dealing with like birds. Coloration, maybe. Maintenance is all about your basic metabolic processes. So your cell respiration, immune system, repair. You get a cut, your body repairs it. That's all considered maintenance. You're just sitting around in a chair, sitting there relaxing, your body's taking part in maintenance. And then reproduction's about energy that's allocated to the reproductive process. So we can talk about size and quality of the offspring. We can talk about number of offspring. We can talk about courtship behaviors, parental care. Key thing, again, we've got a finite amount of energy. We've got this pool of energy. It's going to be allocated to one of these three processes. If we allocate all of the energy to growth, that means there's no extra energy for maintenance and reproduction. If we split our energy between growth and reproduction, then there's no energy available to maintenance. So that's where that finite amount of energy is coming into play. We've got this fixed thing. Once we allocate it one way, it's unavailable to be moved to something else. That decision has trade-offs, and that's going to be a big part of our life history strategy. We've got trade-offs. If we're going to allocate it to growth, more to growth, that means there's less available for maintenance and reproduction, and that can affect our life history strategies. So how do we evolve this strategy? It's all based on, if our strategy is this suite of traits, how do we account for it? So we're going to step back and talk about the evolution section. We talked about best traits, right? You evolved, the panda evolved the thumb. That was a single trait. And it was pretty easy to say, well, if your thumb was if that protrusion was slightly longer than another one, then you're going to do better. We don't have that here because we can't look at one single phenotype. We have to look at the suite of traits that compose that life history strategy. So our interpretation, how we make predictions about what's going to be best, will be quite a bit different. Right? So our fitness that we're going to look at is determined by the overall strategy, not just a single component to it. Yes, a single component is going to influence our overall fitness, but selection's acting on the entire suite of traits. The traits that we talk about, we've got trade-offs between all of them. So just because we increase one and decrease the other doesn't necessarily mean that we're going to cause a drastic change in our fitness. Right? So again, I have this in red. Selection's favoring the overall strategy, not a single trait. And because of that, then, we're going to see, or we can see, different strategies for different situations. All depends on the environment that we're in, those underlying conditions. And there's that contingency again. So how do we compare our strategies using the idea of fitness? We know we can get this. Ready? Again, with the evolution, we could just look at the phenotype. Are we larger? Are we smaller? If you're larger, you do better. Selection's gonna move us in that direction. We can't do that because we're dealing with multiple traits. So, what measure do we use that approximates fitness? A couple people still left. Good. So we have a new term called reproductive value. And this is how we measure fitness. The reproductive value is abbreviated V sub x. There's our sub x. Because it means our reproductive value changes as we age. Reproductive value is defined as the expected reproductive contribution to the next generation of an individual of age X. Expected reproductive contribution to the next generation of an individual of age X. So as we age, our individual ages and moves through those age classes, their reproductive value will change. The equation is this. The equation is this. The sum from t to x, or from t equals x up to infinity, so to the rest of the life of the individual. And it is LTBT divided by L sub x. So we've seen this before. What's that LB? L times B, LX VX. What was that term? What was this top term, LX VX? Actually, let's start with the bottom. What is L sub x? Survivorship. L sub x is survivorship. And this is Vx, that's Lx. So it's survivorship today. Right? So it's survivorship at this time point. If we change this to Lx Bx, L sub x times B sub x, what is that? What's B sub x? What was that in our life tables? That was our birth schedule. What is Lx Bx then? Was our birth schedule and we account for survivorship? What was that? No, not quite. Well, under what conditions? That was our realized reproduction. So birth, if we account for survival to that point. This is realized reproduction. So realized reproduction over survivorship. But it's not just realized reproduction today. It's current and future reproduction. All right, so our equation has current and future reproduction divided by survival today. Because that's what this reproductive value is trying to determine. It's trying to figure out, should we invest our energy into reproducing today because we might not survive to tomorrow? Or should we put our energy into surviving today because the prospects of reproducing are much better tomorrow? And that's our trade-off. That's what this reproductive value is dealing with. And is trying to quantify, or at least give us a proxy for fitness that accounts for all of these life history traits that we're talking about. All right, so the equation we talked about, realized reproduction, that's current and future births relative to just accounting for survival today. Now, mathematically, when we calculate this, this gives us the expected number of offspring an individual will produce today and for the rest of their life. And that accounts for our survival. We have to survive and reproduce later in life as well. But note that this Vx is for our age at a specific time point. So it excludes everything that we did earlier in life. Because that's not what matters. What matters is, what should we do today? Should we reproduce or should we survive because our prospects of reproducing are much better tomorrow? Are we going to calculate this? No, we're not. We could. We've got our life tables. Go back to the life table that we used in lab. Yeah, we can calculate our Vx. And we can make a Vx curve to figure out which age class is most valuable to our population. But we're not going to do it, because I think the key concept isn't necessarily how to calculate this, but it's understanding what it represents and how we use it to predict our life history strategies. So if we were to do it, if we were to actually calculate reproductive value, we would get a curve that looks like a triangle. So Vx as a function of age, we would see our Vx, reproductive potential, increasing as we age, reaches a peak, and then declines. And it's virtually all of our reproductive value curves are going to look something like this. It's going to be this triangle shape. And we can think about, why does it look this way? Well, the peak, we'll start with the peak, that represents our peak reproductive age. That represents peak reproductive age. We are most valuable at this time point because we are now able to reproduce. So we can not only reproduce now, but we also can reproduce in the future. And remember, we count for survival. So we've survived to reproductive age. Now we can reproduce and we can make contributions to the next generation. That represents our peak. That's our peak reproductive age. We increase to it because as we age and as we survive, we are getting closer and closer to that peak reproductive age, which means our reproductive value is going up. If we look at a very young age, at a newborn, their reproductive value is actually fairly low because there's no guarantee that they will ever make it to maturity. But with each successive time period, they've survived it. They're getting closer and closer to this peak reproductive age. And then it declines because now we've passed that peak and we're getting closer and closer to either the end of our lifespan or the end of our reproductive life. So when we get down to zero, where our reproductive value is zero, it doesn't necessarily mean that we've died. Because, yeah, if we die, yeah, your reproductive value is zero. You can't contribute any more to our population. But it doesn't have to mean that we've died. It may be that we've just stopped reproducing. Maybe still living. Fix that. 2 L's. All right, so all of our curves are going to look like this, and they represent the change in survivorship and birth schedules. So if we change our survivorship or birth schedule, we're going to change the curve. Again, it's going to look like this triangle shaped, but it can affect how tall it is. It can affect where our peak is. So our peak is kind of leaning more towards the right. We can lean more towards the left. We could really lean towards the left. We could really lean more towards the right. Right? So it's all going to be affected. The shape of this curve is going to be affected by survivorship, LX, and birth curve and birth schedules. Why? Because that's what's in our equation. All right, so Vx changes with age because of our change in survivorship and our change in fecundity, our birth schedule. So as we said, we're going to be most valuable when we've survived to our maturity, and we're going to be most valuable when we are sexually mature because now we can reproduce not only now, but also in the future. And our life history strategy, everything that we're going to talk about, all the different strategies are going to change the shape of this Vx curve. So we're going to use the Vx curve to make predictions about the best strategy. I'd already said most of this stuff, so just leave it up so you can get it. So just kind of as a demonstration, altering life history strategies. Again, life history strategies represent changes in allocation of energy, how we allocate our finite energy. If we start investing more in survivorship early in life, what we should be doing is raising this line up, making it less steep to get to that peak, because we're making it more and more likely that our individuals will make it to reproductive age. If we invest less in that survival and more into, let's say, growing in size, then in theory, once we hit maturity, we should be larger, can have more offspring, so our peak might be higher. Our peak might be higher because we're leaving more offspring, but it's going to be a much steeper curve because it's less likely that we can survive to that peak. So our fitness utilizes reproductive value. So reproductive value is a proxy for fitness. Selection acts on this, or chooses which strategy wins out based on these Vx curves. And it does so not so much as the peak, where the peak falls, but it looks at the entire curve itself. So selection action favors that strategy with the best overall Vx curve. Again, it's not necessarily the peak, it's the best overall curve. And we estimate our overall curve, or how well our overall curve does, by taking the area underneath the curve. So it's this area underneath our line represents basically overall value. Overall value. So if we have more area, then we should have higher overall fitness for that strategy. And I have this diagram here to kind of represent or give us an example of this. So we have strategy 1. Strategy 1 is such where we're going to invest a lot in reproduction, producing a lot of offspring. Maybe we do it by having a very large clutch size. Maybe we reproduce numerous times over a very short period of time so that we can still produce a large number of offspring. Right? But if we're going to invest in a large number of offspring, and do it over a very short period of time, that energy is now unavailable for both growth and maintenance. So the net result then is that our organism probably isn't going to live as long. It diverts that energy to reproduction at the cost of maintenance. Maybe they're going to be more susceptible to disease. Their mortality rates will go up. So that's strategy one. Strategy number two is this blue line. Now we have a lower peak, probably because we're not investing in producing a huge number of offspring. Also seems a little bit flatter, which probably means we're investing a little bit more in maintenance and survival. And if we're going to survive, probably we're going to reproduce not just one time, but maybe a couple times throughout our life. And kind of spread the risk of our reproduction over time. So we don't have as high of peak at any one point, but our curve spans a much larger period of time. So which one's better? Some of you might say the higher peak, but remember, that's not what we judge. We're not looking at the overall peak. We're looking at the overall area under the curve. And I can see that this area under the curve looks to be a lot less than the area underneath this blue line. So if we had two populations of the same species, and that's what this could represent. We've got habitat 1 exhibits the black line, habitat 2 population exhibits the blue line, and then we put them together. We take the black line, move them over to this habitat, take the blue line, move it to this habitat. We're going to compare these curves, and it's going to be this blue line that wins out. That strategy that wins out because it has the highest area under the curve. But that's a little misleading because if I do that reciprocal transfer study, I'm taking individuals that have adapted to their habitat. This curve does great for that habitat. But as soon as I move it over here, we're going to probably start seeing a change in that curve. Selection is going to start producing different reproductive strategies to fit that environment. So these just represent a snapshot. These curves represent a snapshot of the environment at that specific time. Next year, it could be different. Selection could favor a slightly different curve and so forth. And ask, why is that? Contingency and ecology. Our selective factors are determined by the underlying conditions in our habitat, in our environment. They're going to change. All right, so when we make these curves and we look at these curves, they're only good for that current condition. They can change. All right, so these strategies, if selection is able to act on them, right, go back to Darwin's tenets for this, but our strategies then must have a genetic component. So as long as it has a genetic component, and that genetic component is heritable, then selection can act to start to produce the best strategy, the best life history strategy. But we do see phenotypic plasticity as being a possible part of our strategy. That means that we have one type of strategy. Let's say we go out and look at a population, and we'll say a population of fish. We'll do mosquito fish since they have a shorter lifespan. They can reproduce multiple times throughout the year. If we looked at when they start reproducing, let's say they reproduce at about 3 months of age. That's in habitat 1. If we take those fish and move it to a different environment, maybe they start reproducing at habitat at 2 months of age. And it's not like over time, over 20 years, we see this shift. It's pretty rapid. We move them over, right? We move young of the year hatchlings out, put them in there, they start reproducing at 2 months of age. Was that genetic? Couldn't be. It happened too quickly. That's phenotypic plasticity. So why? Why would some life history traits be favored to be phenotypically plastic? It goes back to our changing environments. You never know what the environment's going to do. So if we are in an environment that changes regularly and those changes are unpredictable, then evolution is going to favor those species that have phenotypic plasticity as part of their life history strategy. For our mosquito fish, perhaps they are responding to predation pressure. So if they sense that they have a high degree of predation in environment 2, then their strategy may be to reproduce earlier. So that try to get to maturity and reproduce before they get eaten. But as soon as that predator leaves, now we're back to strategy number 1. There's no need to hurry up, mature early on in life. Let's wait until we're a little bit bigger and then start reproducing. So note, phenotypic plasticity can also apply with these strategies. All right, so quick summary. Life history strategies have evolved. And the 2 key selective factors that favor this will be our environmental variability and our external mortality factors. All right, so that external variability is that determination for your phenotypic plasticity. The external mortality factors goes into that survival. How likely is it that we can survive to reproductive maturity? If our survival chances are low, we better reproduce as soon as we can. If survival is high, hey, we can delay reproduction. All right, both of these, the environmental variability and external mortality factors, affect the overall shape of that VX curve. And if our shape changes, then it changes what our best strategy will be. Our strategies are influenced by the finite amount of energy that we have. So we had that curve that said we have growth, reproduction, and maintenance. We also have additional trade-offs within each of those. So if we're talking about growth, should we allocate the energy towards fast growth or increase sizes? For our reproduction, should we allocate the energy that we give to reproduction, should we put it towards producing quality offspring, or should we allocate it towards quantity of offspring? All right, so we have this finite amount of energy that we're going to allocate it to one of these 3 processes, and actually we're allocating it to all 3. All right, it's just a question of how much should we allocate, and then each one of these has its own trade-offs inside of it. That's going to be our final lab. The diaspores kind of addresses this allocation of energy. How should we allocate our energy on our diaspores? And then the allocation pattern tries to maximize our fitness. Reproductive value serves as a proxy for fitness. So the more area under our VX curve that we have, the higher the fitness. Less area, we have lower fitness. Or at least our strategies would have lower fitness. And we finish up to talk about how we have both genetic component and phenotypic plastic component. Phenotypically plastic component. All right. Questions? All right. So this is optimization of our life history strategies. Kind of gives us a better idea of how strategies are selected, how evolution selects our strategies. What we're going to do is hit each of our different components. So we're going to start with life cycles, type of life cycles that we have for our organism. That means that with this optimization being done, I think what I'll do is I'll make the quiz for this due on Thursday night. Kind of gives you some time to work on the interaction of regulatory factors for Wednesday night, and then Thursday night you can do this. All right? life cycles, we'll probably finish that up on Wednesday as well. So probably one day. All right. Don't forget lab. Don't forget to bring your leachates.